Hello, I'm Dominic. I am a tutor on Wyzant. I mostly do math and physics, but my background is in engineering. I have a master's degree in the field. And so sometimes I do tutor and help with circuit analysis. In this case, this is a DC resistive network analysis problem. And this question was posted by Oranu and it asks, given that the voltage supplied to the current is 12 volts, so this could be a 12-volt battery. R1 and R2 are both 1,000 ohms, so it could be like 1 kilo ohm. And this is also 1 kilo ohm. R3 and R4 are both 2,200 ohms, or 2.2K, right? 2.2K ohms. How can I calculate the total equivalent resistance of the circuit and using Kirchhoff's laws solve for the unknown currents I1 through I7 passing through and the voltage drops in each resistor? Okay, so the first question is asking how to find the equivalent resistance. In order to do that, you're going to have to use two rules. One is if resistors are in series, which in that case, let's say this is R1, R2, and R3. The equivalent resistance will just be equal to the sum of the resistances. You just add them up. R1 plus R2 plus R3, etc. Now, if they are connected in parallel, which means both of their terminals are connected, this is R1, R2, R3 again. This time you'll have 1 over R1 plus 1 over R2 plus 1 over R3 equals 1 over the equivalent resistance. In other words, if you wanted to find the actual equivalent resistance, you just sum all the reciprocals and then reciprocate that to the -1 power. So we're going to use those two relations to find the equivalent resistance of this network. Now, if I look at my source, it's up in the top left corner. We're looking at the equivalent resistance as seen from the DC supply or DC source. The circuit is drawn a little bit of a confusing way. It turns out that all of this is one node. You can treat all of this as one node. So you can redraw the circuit like this. So here's my power supply. R2 is actually connected directly in parallel to the battery. This is R2. And it turns out that R3 and R4 are also connected in parallel because they're both connected on this top terminal. D to B are connected and E to C are connected. These nodes A, B, and D are all, there's no components in between them. They're all connected. They're all shorted. They can be treated as one node collectively. So I also have R3 and I also have R4 here. But I have R1 connecting from the bottom node of R3 back to the supply. So equivalently, it looks something like this. So I'm going to reduce this one step at a time here. It turns out, again, R3 and R4 are in parallel. So you use the 1 over formula. Well, it turns out if both resistances are the same value, I'll have 1 over R plus 1 over R. That'll be 2 over R to the -1, which gives me R over 2. So the equivalent value, the equivalent resistance is just half that resistance if they're in parallel. If you have 3 in parallel, it'll be 1/3, etc. So 1/2 of 2.2K, 2.2Ks in parallel will be 1.1K. So I could just treat this as one resistance of 1.1K. Now that is connected in series to this 1K. Remember we said that R1 is 1K. So that I can treat as one resistance of 2.1K, their sum. And now I have, oh, sorry, this is just a wire now. Now I have 2.1K in parallel with 1K. So I can just use the formula. It turns out if you have two resistances, it'll just be product over sum. In other words, 1 times 2.1 over 1 plus 2.1 kilo ohms. I can't memorize that, so I'm going to have to put it in the calculator. That'll be 2.1 over 3.1. So like 2/3. 0.667. So that's the equivalent resistance is 677 kilo ohms, which can be rewritten as 677 ohms. 677 ohms is the equivalent resistance. So that's the answer for the first part. Now, the remaining parts of the question is asking how to find the current, all the unknown currents and the voltage drops between each resistor. In order to solve that, you're going to use these laws. First is Ohm's law, which states that the voltage drop across a resistor is equal to the current going through it times its resistance. And if you have a resistor and the current is going left to right, the voltage drop will happen from left to right. The drop happens in the same direction. 2 is Kirchhoff's voltage law. The voltage in a loop, the sum of all potential differences, will be equal to 0. So if I go in a loop, I'll start at the same voltage that I ended at, or same potential that I ended at. And then lastly is Kirchhoff's current law, which says that all of the currents going into a node will add to 0, meaning the current going into a node is equal to the current going out of the node. For example, if this is node A, current 1 is equal to current 2 plus current 3, because the current going in is equal to the current going out. So I'm going to use these three relations to solve this circuit. Now remember earlier that the equivalent resistance of the circuit is 677 ohms. So that means that equivalently, this DC power supply sees 677 ohms if I were to disregard the whole network. You can treat this whole network as a 677 ohm resistor. So we can actually use that to find the current going through the source. So it turns out that we could just do I equals V over R. So that'll be 12 volts divided by 677. 12 volts divided by 677. That's about, we look at the thousands here, that's 17.7 milliamps. So that's the current going through the power supply. 17.7 milliamps. I'm going to write the currents in red. I'll probably write the voltages in green. So that's the current going through here. That's I1, and it's also I7. I1 and I7 are both the same current because they're just on the same branch. Now, how do I find the other values? Well, first what I can start off with is I know that R2 is connected directly to the battery. So I know that according to KVL, the Kirchhoff's voltage law, if I go up 12, I have to go back down 12 to get back to the start of this loop. So this potential drop is 12 volts. It's dropping from right to left. So that means that the current going through here is dropping from right to left. And I could just use V over R again to find the current. That'll be 12 divided by 1,000. So that'll be 12 milliamps. So 12 milliamps going right to left. Okay. Now the next part is that we have here R4 and R3. They are connected in parallel, as I mentioned earlier, because node D is connected to B and E is connected to C. This means they both have the same voltage drop according to KVL. So whatever this voltage drop is from plus to minus will have to be the same as this voltage drop from plus to minus. We don't technically know what it is yet, though. So that part we'll have to figure out. Let's just make some equations here then, because we know that up here we have 17.7 going in to this node. Again, remember we treated this whole thing as one node up here. We have 17.7 going in. We have 12 milliamps going out. That means that we still need another 5.7. Well, that's I4 and I3. I4 and I3 are both going out. I4 plus I3 will have to be equal to that remaining 5.7 milliamps. And if you don't believe me, you could just say, well, plus I5 equals I1, because that's going in, and you subtract, you'll get this 5.7. Well, we know that they both have the same voltage. They both have the same voltage, and they both have the same current. So according to Ohm's law, they'll both have the same current because they have the same voltage across them and the same resistance across them. So I could just say this is equal to 2 times I3 or 2 times I4, because I4 and I3 are going to be the same value. So I could do 5.7 divided by 2. 5.7 divided by 2 is 2.85 milliamps. So that means that there will be, our I4 is going to be 2.85 milliamps going down. And I will also have, this is going to be I3. This will also be 2.85 milliamps. And like I said, their voltage drops will be the same. So I could just do V equals IR and multiply these. 2.85 times 2.2. Remember, this is kilo ohms times milliamps, so the kilo and the milli will cancel. It'll be 6.27 volts across both of them. I forgot I was supposed to write these in green. This will be 6.27 volts. This is also 6.27 volts. Okay, and now we just have this last resistor here. Note that this is a loop. So if I have 12 going up here, 6.27, their difference will be this last drop here. So what I can do is take the difference, 5.73, and that's going to be after going this way, 5.73. And if I divide by 1.1K, that'll be 5.73 milliamps. And that will do it.